Okay, so we are ready to start with our second talk. We are very happy to have Josh Ruderman, who will tell us about pandemic dark matter.
Thank you. Thanks to the organizers. It's my first time talking at a workshop in forever, and I wanted to celebrate that many of us are in person by using the Blackboard. So I apologize to the people on Zoom where it might be harder to see. Okay, so there are already many ideas for where dark matter could come from. So at this point, when is it worth thinking of yet more ideas? And I'd say it's worth it if there's unique experimental prospects, and I'll argue today also if there's unique comic prospects. So, yeah, and indeed, so in late March, we were wondering, like, what can we take inspiration from things in the news for ways that dark matter could be made? And if you think about, say, transmission of a pathogen like a virus, you could think of it as a 2-to-2 process of an infected person that I'll call I. To borrow the nomenclature of epidemiologists, they'll call the other person the susceptible person, susceptible to infection, S. And then that becomes 2 infected people. And then the rate that this is happening depends on the number of infected, because you need infected in the initial stage, so you get exponential increase in the number of infected. So we want to ask, can we do this instead with dark matter? So it's now labeled as chi. I guess we could just keep S. Well, I'll call that psi. Okay. And then this could give an exponential increase in, say, the number density as a function of time. You don't want the process infected to infected susceptible, because that would be nonsense. So we obviously want to be far from equilibrium here. Okay. So that's a question one could ask that we were asking in late March. Yeah, and I'll mention also there's another paper with a similar thought that came out soon after. Okay, so before I talk about how to implement this, I'm just going to give a lightning review of the kind of main paradigms for producing particle dark matter, freeze out and freeze in. So I'm separating, say, classical dark matter will not appear in this talk, like misalignment. So things that are really in the particle limit. There's kind of 2 very big different ideas, freeze out and freeze in. And then what I'm going to describe will be different from both of those, but I just want to review those so that we can compare to them to see how it's different. So we'll start with lightning review. Freeze out versus in. Okay, and these are both very general ideas that I'll just illustrate with an example. So the freeze out would be like WIMP dark matter, where dark matter begins in equilibrium, and then perhaps it annihilates into other states. Although there are many variations of the process you can consider in this step, but the prototypical example would be annihilations. This is described by, so the number density of dark matter is described by a Boltzmann equation. Which depends on the cross-section for this process. And then there are 2 terms that correspond to annihilations and inverse annihilations. Okay. So now what about freeze in? Here you start with a large amount of dark matter. It's in equilibrium, so you have comparable amount of dark matter and photons. Freeze-in is the opposite regime, where you start with very little and you leak in from a thermal bath. And again, there are many processes you could consider, but I'll just take a 2-to-2 example. So here psi will be some state in equilibrium that is, say, annihilating into dark matter. You could also consider decay or whatever. Oh, yeah, and I guess here I'll give this term was from this paper, this famous paper. Here. Okay, and again, this can be described, so the number density of the dark matter can be described by a Boltzmann equation. Well, sorry. Okay. And in this case, since you're assuming very little of this, you can ignore the process in the opposite direction. So that's why there's only one term here, like here, where there's two terms. Okay. And let me kind of stress a little more carefully the difference in the initial condition in these two cases, because in the kind of third case that I'll talk about, the initial condition will enter in a different way. So just to be very pedantic, so what's the initial condition here is thermal. So you assume equilibrium initial condition. And then you solve this equation and you get the answer. If we make a plot of, say, the co-moving number density, which I'll call Y for yield. So this I'll define to be number density per entropy. And say I plot that against inverse temperature. You fall exponentially until the moment where this becomes slower than Hubble, and then you're constant. So it's freeze out. If we compare it to, say, the equilibrium. Okay. And the beautiful thing about this idea is that it's totally insensitive to the initial condition, in the sense that the equilibrium distribution is an attractor. So if you imagine some process at very high temperatures injected or removed some dark matter, things would rethermalize and restore back to this condition. So that's, and then everything happens in the infrared. Okay. So what about this case? So here, the initial condition that's assumed is that the number density starts very small, so that you leak in from the thermal bath. It's the opposite of this case. So you assume initially n chi is much less than n chi equilibrium. But this assumption was not an attractor, and if you would add something, it would deform from that. But anyway, so it's often assumed in papers about this, furthermore, that it's just set to 0 initially, but that's not needed for this idea. But anyway, now you can solve this equation. And you get, so suppose I really start at 0, then you'll increase, and then typically this process will become slow at some point, and then it'll become constant. But here I want to stress that the initial condition is really additive, in the sense that if some process at high temperature not connected to this injected some, then you should just add that amount to the amount that came from this. So here the initial condition is really additive, in the sense that the final value will be given by the initial value plus the value produced by freeze-in. So I can write that like this. Yeah. So if I started, say, here, then I would have got a curve that looked like that. Sorry, that might be hard to see. So in this sense, the initial condition is really additive. And that's different from here, because here, if you added a little bit, it would rethermalize back to the equilibrium. So in this sense, you're really sensitive to the ultraviolet initial amount. Yeah, so you can just shift this curve upward. Okay, so that concludes the review part. Any question about these two ideas? I just kind of want to have them to compare, because now I'm going to say something that turns out to be different. And I think new. Okay. No. Yeah, and the kind of key. So here, right, you start with this thermal bath in the initial state, and you leak in to dark matter, and therefore the amount or the rate that you're producing dark matter is independent of the amount that you have at any moment, or that's why this initial condition is additive, or the amount you produce doesn't depend on how much you already made. So we wanted to look at a different case where the dark matter is playing a role in the initial state. That'll be the qualitative difference, and that's not a property of any of the Friesen models. Okay. But otherwise, it'll be similar. So we'll assume that you start with a very small amount of chi, very far below its equilibrium abundance, but some amount so that this can happen. And then it scatters against a thermal state. So here psi, in both cases, is in equilibrium. Okay. And so that's the idea. And then, so now the initial condition will no longer be additive because the rate that you're making dark matter depends on the amount of dark matter present. That's different. But again, we can write a Boltzmann equation that describes this. And since we're assuming there's very little of these, the inverse process you can neglect. So it's very similar to this. The only difference is one of these psi equilibrium gets exchanged with an n chi. Okay, so it's looks like a small change, but it's a very big change in terms of the behavior of the solution, because now the rate that you're making this depends on the amount present at any time. And then if this is happening faster than Hubble, then it will grow exponentially quickly, the amount that you have, unlike the power law growth that you have here. Sorry? You can consider either ordering. Lighter is simpler in the sense that if it were heavier, this will generically make the dark matter unstable. But that can be okay. That depends on the details.
The way you wrote it, at least, no?
Yeah. So here I mean, this direction.
So exponentially suppressed.
So if psi is heavier, then it's not exponentially suppressed.
But I thought, okay.
You can consider either order.
Okay.
I'm going to focus. So let's just focus, say, on the case where psi is heavier. That'll be a little easier, and then it's not. But either order can work. Just if chi is heavier, then generically this interaction plus other interactions will make it decay, and then you need to pay attention to whether it's long enough lived. Okay. So there'll be some initial condition. Which I'll write like this. And then the picture is that something produced some initial amount, and then at some moment this becomes faster than Hubble and then grows that initial amount to an exponentially larger amount. That'll be the behavior. And indeed, the solution to this equation is very simple. It's just that if you switch to co-moving number density, then it just grows exponentially. So the final value will just be the initial value times an exponent of a rate that I'll write like this. Where R is defined to be this rate divided by this rate. Okay. Yeah, and here I'll take this x variable to be inverse temperature. You can use either mass. I'll normalize to the mass of the thermal state. Okay. So this corresponds to exponential growth, and unlike here where the initial condition was additive, here the initial condition is multiplicative. That's what exponential growth does. Okay, so multiplicative. Yes. Yeah, I'm gonna write an example in part 3, but it'll be sort of a toy with scalars. And then at the sort of end, I'll mention ongoing work on.
The number of particles that you have in the light state grows exponential.
You mean if it's stimulated, or if you just have decay, the rate you're decaying doesn't depend on how many you've decayed so far.
But the number of particles you had initially decays exponentially.
Oh yeah. So decay removes things exponentially. Here you grow things exponentially. That's the difference.
I mean, if I look at it from the light state point of view, it's like they are growing exponential. So I don't understand. From a decay.
No, because again, the rate doesn't depend on how many light states are present. So if I have decay, it's just a constant rate. So decay would be an example here. Yeah, so like for 2 to 2, the rate is n psi equilibrium sigma v. You could also consider, indeed, you could consider decay. So that's like a classic case for freeze-in would be freeze-in from decay. It could be, well, this could be something else, whatever, right, x. Yeah, now you'll have the following equation, n dot 3h and chi equals n psi equilibrium times the decay rate. But this doesn't depend, this rate that you're making n chi doesn't depend on n chi. That's the difference.
Okay.
But yeah, so the decay would be an example of what I'm calling freeze-in. Okay. So a fun fact is, yeah, indeed. If nothing cuts off this, you will exponentially grow in number until you thermalize, until you reach equilibrium. I'll give an example where it's cut off by this mass threshold so that you can get the right amount of dark matter. That's a very important observation that you're anticipating. Okay. So yeah, what you want is this to be faster than Hubble for a period of time and then not faster than Hubble. Yeah, and I think that's generically, this is thermalization, and then if you arrange things carefully, you can just have sort of a failed thermalization where you end up with dark matter. Indeed, what this wants to do is bring this into equilibrium. Okay. So in physics, we like dualities, and we noticed that this differential equation has an exact duality with an equation used in epidemiology. So let me make that precise. Sorry? I couldn't hear, but masks. Okay. Well, we don't really need to say more. Yeah. Yeah. Absolutely. Okay. So in epidemiology, there's something called the SIR model, and that's where this R number that you read in the news comes from, and this goes back to the 1920s. So when our field was thinking of quantum, they were thinking of number of sick people. And you can write it. So if you call I the number of infected, yeah, so S is number of susceptible people in a population, I is the number of infected people, and R is the number that have recovered. But really we'll care about these two letters. And you can write a differential equation for the number of infected people. And there's two things that change that, either infection or recovery. So this is infection. So beta is the rate of infection. Okay. And gamma is the rate of recovery. Okay. And then the famous R factor corresponds to the average number of susceptible individuals that infected individual infects before they recover. And that's given by beta S over gamma. Okay. So we observe that this is the same equation as the Boltzmann equation. So in this sense, there's an exact duality. If you make the following identification, I and chi, S and N psi, beta and sigma V and gamma and 3H. So here you recover by joining the Hubble flow. But with this identification, it's, yeah.
I don't see the minus gamma in your equation.
Oh, I'm moving the Hubble to the right-hand side. So.
Okay, you can think in that way, but.
Yeah, that's exactly.
But if you write in terms of the yield, just you have beta.
Sorry?
If you write in terms of the yield.
Yeah. But
so it's
epidemiologists are not working in co-moving units.
I understand, but okay.
But I agree. They should, and that is. So anticipating that is what I defined R up there, and then indeed the 3 is. Oh, you can add other. You can add other terms. Yeah. Sure. You can add more terms. Okay. But indeed, you see, the duality can lead you to new thoughts in dark matter space. Okay. So that's warm up, and now I'll give sort of a toy example. Okay. Any questions? So it's just exponential growth. And it's equivalent to this SIR model. Okay. This will be. Yeah, and the precise definition of toy here is that I'm happy to take questions, but if Mina asks too many questions about the model, then I'm going to cut the conversation off and say it's a toy. So anticipating what's about to happen. Okay. That's why I wanted to be precise. But I am happy to take questions. I'm just reserving the right to cut that off. But I encourage questions, so I don't mean to be discouraged. Okay, so just like the stupidest, oh yeah, we're gonna want this to not be faster than Hubble and then become faster than Hubble. So we're gonna want it to be an infrared dominated process. So I'm gonna work with marginal couplings. And if I just have chi and psi, then a simple way to do that would be real scalars. If they're fermions, then you would need a mediator for it to be an IR dominated process. So I'm gonna just take them to be real scalars with a mixed quartic. And then they're both massive. Yeah.
Do you have any other terms to write?
These are the only terms I'm going to use, but there are terms that could be dangerous or fine. So
for example, I'll tell you, by given the symmetry of the Lagrangian that you write, why aren't you writing a psi cubed chi term? That's satisfied by all the symmetries of the
psi squared?
Psi cubed chi.
Psi cubed chi is not going to matter. Yeah, so we can write that. That's fine.
And psi squared and psi squared chi squared.
Psi squared chi squared, I'm going to assume is much smaller than this. That's important.
But then what is the justification for that?
Yeah, so indeed, we can say, let me call this, this will actually, I'll call this lambda fi for a specific reason. So psi squared chi squared, and I'm going to want to be in the limit here where this is much smaller than lambda. This is important.
How do you ensure that?
Yeah, so the simplest, if it's just two Z2s, well, you could have two. If I have a separate Z2s, it would be okay, no? So if I have a Z2 cross Z2.
Then you will make lambda, you can make lambda smaller than lambda fi, but not chi squared.
Okay, sorry. So yeah,
but you
real,
have
not real
the
scalar.
masses. So there are the masses.
Yeah, with real scalar, I can't forbid it with the symmetry. The picture I have in mind is the two sectors are decoupled, the chi and psi sectors, and then the leading coupling between them is this interaction. And then it's technically natural for this to be of order this square.
Yeah, that may be.
Maybe. But yeah, this is radiatively generated by this, but this is of order this squared. Yeah, so you will generate this of order lambda squared over.
I think Rafael's answer is more, yeah. Yes, so there's going to be something proportional to the masses as well.
Oh, okay.
Okay.
Okay, Rafael says is E4. Sure. I just wanted, you could have two things that are decoupled and you can couple them and ask what does that now generate? And in that sense, it's like a super selection effect. Okay. For canonical. Yeah, indeed, because they're real scalars. This is why I don't think.
So then what symmetry do you have?
Super selection. Just states can be decoupled.
What does super selection mean? Like you need, I mean, I'm sorry, but this is the part where we disagree about what toy is. I consider a toy particle physics example something that's self-consistent, meaning I write whatever terms, I have symmetries to explain whatever my couplings are, make sure it's consistent with cosmological constraints. This is what I consider a proper toy example.
You can have different sectors that are decoupled, and then you can add small couplings. We do this with a photon, dark photon. You can ask why is the kinetic mixing not one?
Okay, write the full theory. Right? Okay, waiting. Write the full theory.
This is definitely where I can point to toy. I will mention an example with fermions that we're working on, but it's it's technically natural to break particles down into different groups that couple and then to look at couplings between them. It's what we do with a photon and a dark photon in small kinetic mixing, or if we have h squared times another scalar and we take the.
So Josh,
to be
I mean,
small.
you're on the board, you can write those up. Because what you're writing does not satisfy the symmetries.
The super selection states.
I don't know what does super selection mean? Super selection of the theorist that I pick whatever couplings work for me.
It means there's a point gray group acting on one and then a point gray group acting on the other, and they couple gravitationally, and then you can add interactions that couple
Gravitationally,
them.
you won't get large couplings that you need if it's gravitational.
Oh, no, sure. I'm saying that that's the only way they have to couple. So I'm just taking this to be the leading coupling between two decoupled sectors, the chi sector and the psi sector.
Why don't you write? I'm telling you, like the first coupling I will write down the moment I have two massive scalars is psi squared, chi squared, because that preserves the symmetries.
Sure, I agree. It's exactly analogous to taking a small exponential coupling. So if there's a new, if there's a real scalar, it doesn't have to, one point of view could be this coupling has to be big, and this has to be one. But you could also consider the case where this is small, if S is a sequestered sector from the standard model. So I think there could be different.
How do you make that small and not make also chi cubed small? I don't understand what you mean by.
No, but you can postulate, if you postulate this, right?
You can postulate
No,
whatever
but
you
then
want.
you have to ask what is radiatively generated, right?
Yeah, that's the precise tense. I mean, technically natural, and this is generated of order this squared. If this is a leading
So
couple.
of course you have gravity, but
Oh no, but if I can write a mass, why can I not write a quartic? So
There is a scheme, right? There is a Thompson scheme. So you don't see it in real space, but you see it in Fourier space. So the free Lagrange of a scalar with a mass has this infinite tower of symmetries in momentum space, which can interaction waves in a different way. Yeah, I mean, I don't want to go to the next one. We can do it later. But a free scalar with a mass as a symmetry.
This is another concept theory.
These symmetries, yes, but the selection rules of these symmetries are broken by this psi chi cube in a certain way. And so that's what's enforcing what Josh is saying. That, if you write just that Lagrangian, then you generate the other guy at the lambda square level. I mean, there is a symmetry reason why if you write just that Lagrangian, you get the coupling that Josh doesn't want, but you want only at that level. Of course, I mean, then the needs are.
But I don't know, but there should be a specific, you should be able to see it at the level of Lagrangian, then that is the symmetry that forbids the chi cubed and psi squared chi squared is not generated. Then what is the symmetry for the real scalars?
The symmetry is already broken by psi chi cubed, but in a certain way. So there are selection rules that tell that you're breaking it only from by psi cubed, then the other guy is generated on the level of what you say.
Do you think if there's a hidden photon, it has to kinetically mix with kinetic mixing one with with hypercharge, or?
I don't know what you. Yeah. But,
yeah. Okay. I think that's a reasonable. That's if your point of view is all couplings are one, then.
But there is a way to generate kinetic mixing. So. Okay, maybe there is a super selection symmetry, but I would like to see that symmetry, what the symmetry is, that clearly, if from a particle physics point of view, there is no symmetry that forbids the chi squared, psi squared.
If there's heavy states, the couple.
While there is a symmetry that forbids the chi cube, the psi chi cube term.
I think you're taking this toy model extremely seriously. Make it more than a real scalar and add symmetries. It shouldn't be hard. You just want to have a 3-point coupling and not the 2-point coupling.
But the point about this is to also show how generic of this is to happen. So if there is some weird things happening, some weird corner of parameter space for some models, why is this interesting?
It's a new behavior different from freeze-in. It depends on initial condition differently. It should be easy to realize it.
But that's
building models it would be interesting to do.
But that's precisely what we are debating here. You say it's easy, but you don't have a model.
you can take it to be a complex scalar with a
Then
ZT.
write the full theory. If you don't, please don't tell me words. Please write down a full Lagrangian.
No, but what
that
is
satisfies
what is wrong about this Lagrangian? Here, this.
So I, as a particle physicist, I don't see a symmetry in this Lagrangian.
No, but
for piece the psi squared chi squared.
No, but you can ask, okay, I start this Lagrangian, and then I radiatively generate everything else, and that is a completely consistent theory, right? And then, of course, because of what Rafael said, it's just not evident at the level of Lagrangian that will not forbid this term. And of course, to gravity, then you run into all the problems. The level of a QFT, this is a perfectly fine QFT. And if you add this term with lambda at lambda squared level, because that's how it's going to be generated by loops.
Okay. Sure.
Toy. Yeah. I think we're taking, I really mean it as a toy in the sense, you want some theory with chi psi to chi chi. You don't want psi psi to chi chi to be the same size. I think it would be interesting to do more explicit model building with symmetries. I completely agree. Okay. And just to give you an idea of sort of example parameters that'll work, if we take these masses to be GeV-ish, then I'm going to want this lambda to be about 10 to the minus 6. Okay. Okay, so yeah, and this begins in equilibrium. Oh, yeah. Yeah. Sorry, can you say the assumption again? Yeah, so there's some other interactions with just the size in the psi sector. So this would be L. Oh, sure. I'm assuming this is the dominant way that chi couples to the thermal bath, indeed. So indeed, once psi has interactions, then this will imply interactions for chi, and I'm assuming that this is the leading one. So for example, if psi just annihilates rapidly to some other state, then this assumption will hold. Yeah, so the simplest thing would be maybe psi rapidly annihilates to even standard model psi. Okay. So remember the R factor is 3. Oh, no. And psi sigma v over 3h. And this is going to go like temperature. So this is IR dominated. So if we make a plot of R versus psi over t, it's going to rise like say t to the minus 1 until you cross the psi mass threshold. And then this becomes exponentially small by Boltzmann depletion. So this will then sort of fall exponentially. And if you choose the size of this cross section so that this, if the series 1, you want this to cross 1 for a period of time and then turn non-relativistic and shut off so that you have exponential growth. So in this sense, you can regulate the exponential growth as Savas was anticipating. If this continues for too long, then you're going to just, the exponential very quickly leads to the same number of chi as photons. But if you hit this mass threshold, you can shut that off. That's an example of how you can regulate this. Okay. And here, this coupling will, well, as we were discussing, this coupling generates this coupling at one loop, and this will imply some amount of freeze-in of chi. So there will be some amount of chi produced initially from freeze-in, and this will set sort of a minimal initial condition, where you could then consider other contributions. But for the initial condition, y chi 0 will minimally be produced by freeze-in. Yeah, so you have for example, this 2 to 4 process. Or you can close the loop. Okay, and this will, so these both have cross section. These are the same size parametrically, and they imply some amount of freeze-in for chi that is going like lambda to the fourth in the cross section. Oh, sure.
So that the rate is proportional
It
to
will,
lambda squared.
but suppressed. If you're looking at what's generated here radiatively by an amount suppressed by lambda squared.
No, that process will be lambda squared. It will be the mixing will be lambda. It's just a loop. Close the loop of chi. Psi goes to chi, and then psi couples to the standard model, and then you have a process that thermalizes chi at the order of lambda squared.
Help me. Okay. Sorry, which loop?
Close the loop of the.
Oh, sure.
Depends on how psi couples to Higgs, because that fixes it.
Okay, that's fine. So you want to say there's a lambda
There's a
size mixing?
yes, chi psi mixing. That's still and the time, and it's also a cutoff dependent.
Yes.
So then that will also mix. If psi couples to the standard model, that will mix with the chi with the standard model, and then you will have processes that are proportional not to lambda to the fourth, but to much lower order.
Yes. Let's see. So if we do say psi squared h squared, then to literally get a chi squared, I would need 2 of these. But yeah. So I can this if I have psi squared h squared, I need to mix twice, and then it's lambda squared. If I mix once, then this contains a chi. So it doesn't freeze in because it needs a chi in the initial state.
Thermal equilibrium. Yes, it can be produced. You have chi psi scattered into Higgses, and the
but that's smaller than just chi psi to chi chi. It's by a loop.
No, sorry. You want to see, you need to check. This is a process with which chi couples to a thermal bath at order of lambda squared.
Yes. Okay.
Yes. Yes.
Yes, that is a good question.
Right?
Say GeV scale. If this needs to be smaller than this for this to dominate, but indeed, yeah, this is dangerous, I think. I think yeah, indeed. I think if you mix in of size lambda, it's still maybe okay. Because at worst, this is competitive with this, right? Yes. Let's discuss after. I need to think about the implication of kinetic mixing. But oh, I don't. This is just an example. I could just annihilate into something, but psi needs to be in equilibrium. So you could ask, given yeah, you don't want too much freezing. Okay, so I need to think about this kinetic mixing. Okay, so given, we'll start with some amount, which we're arguing about how much. Enter period of exponential growth until you hit this mass threshold and then flatten. That's what we see now. And because of the exponential growth, the final abundance is only logarithmically sensitive to where you start here. So sort of the size of lambda you need will go like log of y0. So at worst, it's logarithmically sensitive to pushing around this value. And then for GeV size masses, this will work for lambda of about 10 to the minus 6. Okay. So that concludes the example. Should lead to some interest. And I just want to conclude by mentioning a couple of things we're thinking about now. Okay. So one idea towards having a model that's not just real scalars is to do this with fermions, and specifically, we're looking with Jorn Kirsten at whether you can do this, whether you can make sterile neutrinos, but by scattering against active neutrinos. Okay, so consider sterile neutrino mixing with active neutrinos, and you get some production from oscillations into steriles from Dodelson-Widrow. And suppose the mixing is too small to produce the observed amount. If you have, say, self-interactions among steriles, then you can mix once. And consider, so now you can have sterile plus active goes to sterile sterile, and this will exponentially grow the number of steriles. So you could produce some from oscillation from the standard model bath, and then exponentially grow that amount by scattering against actives. Okay, so this is sort of in progress. And here the mixing is just controlled by theta. Okay. And one other kind of question mark is, well, this exponential growth in principle allows a large amount of energy to be liberated, well, in this case, from psi states to chi states very quickly. And if this could happen in the universe in an inhomogeneous way, this could potentially give something like gravitational waves. It's sort of a different type of phase transition. So this we're looking at with Michael. Can you have a situation where, if this is your Hubble patch, you have sort of several domains where you're exponentially growing the number of states? Out of some sort of bath of psi, and then maybe this could be some, if it's at least a order one amount of energy density at this moment in the psi's converted to chi's, then a small number of seeds would produce some inhomogeneity. So there could be some sort of particle interaction ways of looking at very inhomogeneous phase transitions. Okay, so that's just some things in progress, but I'll end there.
More questions?
I really love the analogy with the epidemiology, but I think in the SIR model, there is a conserved quantity, which is the total number of people. So you can exploit that maybe to close the system and avoid, maybe less ambitious, but it can work as a recombination process.
Conservative if it doesn't kill you. Yeah.
Huh?
Conservative except for death and birth.
Okay.
No, that's
Any questions? Any other questions? Okay. If not, let's thank Josh again.